Vanakkam. Welcome to this course on biomedical instrumentation. In this video, we will look at generalized measurement system, what are the static and dynamic characteristics, what are the types of systems and what is the frequency response and what are some of the time domain parameters. We will introduce ourselves to these notions. Some of these things we will continue to discuss in future videos and weeks in more detail. So, what is generalized measurement system characteristics? What are the various characteristics of this measurement system? Usually, a generalized measurement system consists of several functional blocks, each of these functional block has its own transfer function. What is a transfer function? What is a transfer function? I am not going to answer that. You will find out the answer. Each of this has its own transfer function. The output of one of this block serves as an input to the next block in a logical sequence. The purpose is to acquire, process, display the measured data, physiological data. The overall performance of the system is of course affected by the individual characteristics of these blocks. Individual characteristics matter, right? It is also intricately linked, it is also affected by the collective characteristics. How do these systems work together? That also matters. So, individual contributions matter, team contribution also matters, both of these matters. Collective characteristics also matters, right? The initial sensing element, it may be a transducer or it may be a sensor. What is the difference? We have seen many times what it is. The initial sensing element or a transducer is perhaps the most critical or particularly important to the performance of the system, because if it is noisy, then there is no way for you to remove that noise. So, the initial one must have minimal noise. By definition, it should have minimal noise. So, what are some of the critical design considerations? What are some of the critical considerations? Impedance matching, noise factor, dynamic range. These are some of the critical design considerations. Right. This is a generalized measurement system. For example, there can be an active procedure such as excitation, transmission, illumination, irradiation, stimulation, application are one of these injections. So, suppose the object of measurement, so, say for example, ECG, you are interested in heart function, right. So, that heart, oops, some problem. So, heart, I am keeping an electrode to measure the electrical activity, and then I am amplifying it, and then I am displaying it, right. So, the input signal is a physical or chemical quantity, in this case an electrical quantity, sensors, and then the signal is also an electrical quantity. In the case of heart ECG, it is an electrical quantity that is getting sensed, electrical quantity, and then there is an electronic instrument that then is displayed to the observer, display. Right. What are the key characteristics of a measurement system? Static characteristics. The static characteristics describe performance under constant, but there is no such thing as a constant input. Usually what this means is a relatively slowly changing inputs. Accuracy, which indicates the closeness of the measured value to the true value. It includes all forms of error. So, it is not for you going to classify different types of errors. It is going to include all forms of errors, systematic errors and random errors. And it is usually expressed as a percentage of the absolute, percentage of the full scale value, or as an absolute value in units, in the corresponding units. Precision usually refers to the repeatability or consistency of measurements. a precise system may or may not be accurate if there is a bias. Here are some examples, right. Situation A refers to is an ideal situation in which a system that has high precision and high accuracy. If this is the true value, it is highly repeatable and it is also very close to the true value, high accuracy and high precision. This one C refers to a situation in which the accuracy is good, but the repeatability is not good. This is C refers to high accuracy but low precision. That means there is random noise or random errors. B refers to a situation in which the repeatability is very good, but the true value, it is far away from the or relatively far from the true value. That means B, low accuracy and high precision. Right. That means what? That means there is a systematic bias or systemic bias. D refers to a situation in which there is low precision and low accuracy. Low accuracy and low precision, which is the worst possible situation. Right? Something to keep in mind. What are the various considerations? Linearity. How closely the input follows a straight line relationship, how the output and input are related with through a straight line, y equal to mx plus c or whatever, right. Any deviation from this linear behavior is considered non-linearity. For example, these are non-linear responses. Then sensitivity. For a given small change in the input, by how much the output is changing, ratio of the output change to the input change, that is delta y by delta x, where y is in the output and the x is in the input. A higher sensitivity means the output changes more for a small change in the input. Right. Resolution essentially refers to the smallest possible change that can be detected, that the system can properly identify. Hysteresis is a form of nonlinearity that occurs when the output depends on whether an input is in the increasing direction or in the decreasing direction. Actually, the direction of loading or unloading, the direction should not matter. If it is a linear system, that will not happen. In nonlinear systems, this happens. Drift, this happens a lot in biomedical systems. This essentially refers to an undesired observable change in the output over time. For a constant input, output keeps on changing. This is called drift. This may be due to temperature change, or this may be due to power fluctuation, this may be due to aging, or this may also reflect sensor characteristics. Some sensors are inherently drift prone. For example, piezoelectric sensors. There are several other sensors that are inherently prone to drift. Right. Reproducibility or repeatability is the ability to produce the same output for the same input under identical conditions, but it is not clear what is an identical condition. What do you mean by this? There is no such thing as two identical conditions. From an experimental perspective, it is not clear what one means by identical conditions. Threshold is the minimum level of input that is required to produce a measurable change in the output. This is the smallest change, that is smallest change in the input that causes the first measurable change in the output. Then you have dynamic characteristics. What we saw till now are static characteristics. Then you have dynamic characteristics. These are essentially how a measurement system responds to inputs that change relatively fast over time, rapid changes in time. This refers to input output behavior during transients or time varying conditions. Transients mean things that change relatively quickly. Contrast this with the characteristics that happen in static systems that deal with steady state or relatively slowly varying inputs. Right. Dynamic characteristics are absolutely critical for accurate waveform detection, reproduction or control systems. Right. In physiological systems, it is especially crucial for measurements such as EEG, ECG or blood pressure waveforms that are inherently time varying, that are dynamic in nature. And then there is time constant. This indicates how quickly the output changes to an abrupt change in the input, the time constant. And a frequency response describes how the system's gain and phase shift change the frequency, change with not change the, but rather change with the frequency of the input signal. As the frequency changes, how does the input and output changes? It is called frequency response. We know from basic electrical engineering how to measure this. And then you have accurate dynamic measurements. So, accurate measurements of dynamic signals are only possible if the frequency components fall within the system's effective frequency response range, that is within the bandwidth of the system. And there is a natural frequency of a system, or resonant frequency is a critical parameter. For accurate measurements, it is important to have input signal frequencies that are well below this natural frequency to prevent distortion or undesirable oscillation, because if you are at resonance, then there will be oscillations, that will, you must work well below this level, right. Then what are the types of systems and frequency responses? Linear versus non-linear systems. So, in the linear system, the sum of individual inputs cause the output of the summed input. The output of the sum of individual inputs will actually be the output that is similar to the summed input, to two different, that is a summed output, a summed input match, that kind of situation. That is output of a sinusoidal input is a sinusoid of the same frequency, not necessarily the same amplitude, of course, the amplitude will vary. A nonlinear system may have higher harmonics because the amplitude will change, and the real systems are mostly linear if the input range, in small ranges usually you will have linearity in relatively small ranges, which is why it is important to define what is your dynamic range. Different measurement systems may be specialized for different frequencies, and you are interested in keeping that dynamic range. So, which means that you need to understand the physiology, physics and the frequency response very clearly. Frequency response essentially refers to amplitude and phase shift for sinusoidal inputs, useful for analyzing and characterizing linear systems using Fourier decomposition. For example, also if you are looking at a first order system, for example, you know this A1 y dot plus A0 y of t is x of t, or a second order system, for example, A2 y double dot plus A1 y dot plus A0 y of t is x of t, for example. The behavior will vary with the damping coefficients. There are cutoff frequencies. We know all these things from our fundamental understanding of engineering mathematics and differential equations. Right. And in time domain, step response matrix matters. A sudden change in input from 0 to 1, for example, will cause what? The output. Time constant. A parameter, a critical time domain parameter is a time constant. The time to reach 63.2% of the final value, the first order, this is A1 by A0. Rise time, the time it takes for the system to go from 10% to 90%. Response time, the time to reach 90% of the final value, and settling time, time to stay within 5%, plus or minus 5% of the final value. These are called as time domain parameters. Then system behavior. Usually first order systems will have a relatively smooth exponential rise. If there is a second order system, they may show overshoot oscillations depending on the value of the damping coefficient. Right. So, with this we come to the end of this video. In this video we looked at a generalized measurement system, static characteristics, dynamic characteristics, frequency response and system types, and some of the time domain parameters. And critically we need to understand the difference between accuracy and precision. Accuracy and precision are not the same, right. And not all measurements are not all physiological signals are linear. Physiological measurements are linear, okay, and there will be a difference in static and dynamic, okay. There will be, and it is important to understand what the bandwidth is, what the hysteresis curve is, okay. And note that time constant tau is the time taken to reach 63.2% of the final value. It is not the total time of final value. Remember this, time constant is the time it takes to reach 63.2% of the final value. So, with this we come to the end of this video. Thank you very much for your attention.